sir. It is with a pleasure to be with you today in order to deal about dhouib-matrix. So dhouib-matrix is a new kind of optimization concept in order to solve combinatorial problems. Scheduling problem is a combinatorial problem, also assignment problem. And here the shortest drilling path in printed circuit board is also a famous combinatorial problem. It is classified as a traveling salesman problem in the field of operational research. So here we have 452 holes in printed circuit board, and I would like to drill all these holes using a computer numerical controlled machine. So here we'll use a robot arm, and for this robot arm there is a starting point, and we would like to minimize the movement of this robot arm in order to visit all these holes only once and return to the starting point. To do this, we need some optimization methods in order to generate a planning for the whole drilling path. And then we will generate a G code which will be inserted into the computer numerical control machine. Our contribution is here in the optimization methods. So in fact, we invent a new concept, and we call this concept as dhouib-matrix, and which is a kind of optimization methods. Optimization method can be classified in two categories: exact methods and approximation methods, where the approximation methods can be heuristics or meta-heuristics. And as I said, the dhouib-matrix will gather the approximative methods, which that means we will generate several heuristics and meta-heuristics. For example, for the heuristics, we generate the DMTSP1 in order to generate the shortest cycle. As the example as I get for the traveling salesman problem, for the finding the shortest path for the TSP. Also, we generate the MEP1 for the assignment problem and the MTP1 for transportation problem. And also we generate several meta-heuristic such as the Fortuner meta-heuristic, DM3 and DM4. Today I will present a step-by-step application of the DMTSP1 heuristic and a quick representation of the DM4 and the Fortuner. So I will start by step-by-step application of the DMTSP1. And for more larger instances, we invent a new meta-heuristic entitled DM4. And to solve multi-objective optimization, we generate a new method entitled the multi-objective DM4. And then in section 4, I will present other new methods. In section 5, I will give a conclusion, and finally, I will present our perspective and what will be our next work. So let's begin with the first method, the dhouib-matrix TSP1. So I will return to this example, and I will show you step-by-step application of this method, and you will see that the DMTSP1 is very quick method. It needs only an iteration in order to generate a solution for this problem. But remember, for this problem, the number of realizable solutions for this number is huge. It would be represented by 2.4 exponential 976 realizable solution. So how we can generate an optimal solution from these huge numbers? So for that, we will present the DMTSP1. So for this problem, actually, the input data will be the geographical position of the holes For example, for the whole number 0 here, the coordinate x will be 10 and the y will be 60. The whole number 1 with the position 10, 10, and so on. So we will use this input data in order to generate a graphical representation of the holes. But if I would like to look for shortest cycle between all these holes, we need to generate a matrix like this, where we have in this matrix we will compute the distance between all these holes. For example, the distance between all number 0 and all number 1. We will use this matrix or any other matrix, for example, Euclidean distance or any one. But here for the Manhattan distance, it is very easy. Just we will compute the distance between all number 0 and 1. So x0 minus x1 plus y0 minus y1, and we will obtain 50. In fact, if you have the matrix distance or this matrix, we can apply the MTSP1 in order to generate the cycle. This method is very simple. It is based on 4 sample steps, where step number 1 and step number 4 are iterated only once, and step 2 and 3 are iterated n-2. So I will go slowly, step by step, the application of this method. So we have the distance matrix between all holes. Here I take just 6 thirds or 6 holes in order to simplify the example. So the first step is to compute the sum for each row. So for this row, I will use the sum function. And then I will select the smallest value, which will be 156, then which correspond to row number 4. Then I will return and select the smallest value of row number 4, which will be here the value 11. At the element position D4, 3, that means row 4 and column 3. So for that, we will insert in the list city the position, that means the city 4 and or the whole number 4 and the whole number 3, and we would like to visit these holes. So for that we will discard column number 3 and column number 4, which is represented here by the red bar. Graphically, we just generate a link between city number 4 and city number 3. Now we can start step number 2, and for step number 2 we will select the extremity bound for the least city, which corresponds to the city number 4, which means row number 4, and we will select the smallest value, row number 4, and again the small value for row number 3. And then we will choose the smallest value, which is here, and at the position D3, 2. So we start the step number 3. We will insert city 2 just after city 3. So like this. And we will discard column 2 in order to eliminate the return to this position or to these holes. Graphically, we just make a link between hole number 3 and hole number 2. We take this condition, go to step 4 if there is not any column, but we have more column here, column 1, 4, and 5. So here we will return to step number 2. Step number 2, we will select the extremity element of the list city. That means the first one and the last one. So for the first line, we should index as to row number 4, and we will select the smallest value for row number 4, and we repeat the same thing for row number 2, and we will select the smallest value, and we will insert here all number 6 just before all number 4, and we eliminate or we discard column 6 in order to eliminate the visit of this hole, and graphically just we make a link between city number 4 and city number 6. Again, we have this condition. We have 2 columns here, so we return to step number 2. Again, we will select the extremity of the list city, which that means the first and the last element. So for the first element, it will indicate for the row number 6, and we will select the smallest element here. Okay. And we will repeat the same treatment for the last extremity, and we will select the smallest value, which will be here 50. So next step, just select which is the smallest, and the position here is D6 5. That means we will join the whole number 5 from the whole number 6. So automatically we will insert the whole number 5 here, and we will discard this column, which is represented here by the red column, in order to eliminate to this city. Graphically, just we make a link here between the 2 all number 6 and 5, and still have a column here, so we need to iterate again step number 2. The same thing, select the extremity bound, the smallest value, which is here. That means we will join city number 1 from city or alls number 5. We will insert all number 1 before all number 5, and graphically we make a link like this. Now there is no more column to discard, so we need to go to step number 4, and using step number 4 we will generate a cycle, and we will close this path. So for the last cycle, just here we add another element, which will the first city. That means we will start and we will finish with city number 1. So here this heuristic needs just an iteration in order to generate an optimal or near optimal solution. Using this technique, we apply the MTSP1 for several problems with crisp data, with fuzzy, intuitionistic, and also nitrosophic environment. And as an extension for the dhouib-matrix TSP1 method, we have this reflection why we use some function, but we can use any other descriptive statistical metrics. We can use mean, max, range, or any other descriptive statistical metrics. And here we have the idea to generate a meta-heuristic. We call this meta-heuristic as DM4, where in DM4 we will not look for which is the better descriptive function, but how we can combine all of them in multi-structure technique. And the DM4 will be used for more large instances. So with the DM4, we will select the majority of the descriptive statistical technique, and we will use then DMTSP1 followed by far too near local search technique for the intensification. So here we repeat the application of DMTSP1 with several statistical metrics. And we apply DM4 for several instances from TSP library, and we compare it with the most famous meta-heuristic in space. You can see here the genetic algorithm, and you can see the ant colony algorithm, the particle swarm optimization algorithm, and this graph represents the deviation, the relative error to the M4. So we can see, we can just conclude for this part that the M4 is good for the TASP problem, but we need to prove the performance of this method to other problems such as assignment problem or scheduling problem, and so on. Also, we apply the M4 for integer distances, and you can see here a 3D representation of the deviation of relative error. Also, we apply the M4 with real distance, and you can see the comparison to ant colony algorithm, hybrid algorithm, and so on. I go quickly through these slides. Also, we test the performance of the M4 for multi-objective optimization. So for mono-objective optimization, we are looking to generate only one solution, but when we deal about a multi-objective problem, we look for a Pareto non-dominated set solution, which we represent here. For example, if I have a distance and nose objective, so here we will generate a set of non-dominated solutions. We call them as a Pareto. So how we can apply the M4 to generate this Pareto? The multi-objective DM4, we will work here in two phases. At first, we will use a dynamic modification of the weight, and you can see here the first Pareto non-optimal dominated solution, and you can see there is some gap here and here. And to intensify this Pareto, we will use a second phase, and here we will select some bounds from the first Pareto in order to generate the second, but in this with the second phase, we will use balanced lexicographical resolution of the objective function. That means sometimes we use F1, the first objective, then the second objective, and the other time we replace them, and we will start by the second objective first, then the second one. We compare the result with the random weighted ant colony algorithm. The M4, the generated solution generated by the M4 is presented by the blue color, where the ant colony optimization technique are represented with red color as here. You can see that the M4 generated good distribution over all the Pareto optimal front. And also we compare the M4 with the exact Pareto solution. So by comparing the M4 with the solution generated by Flores and Mavortas 2014, where they generate an exact Pareto solution, you can see that the M4 generate is almost close to the solution, but there is still some gap here and here. I'll just here present other methods that we developed. We generated another technique. We call this technique as Fartonier. It is a local search method. It is a very fast technique. It is organized on use 3 sample structures, where we use an organized neighbor selection and 3 perturbation techniques, and we will also threshold accepting criteria, and we apply this method for several standard problems. Also, we study the optimal circuit path when changing the position of the starting point. What if I will start my robot arm from this position, or what if I will start my robot arm with this position? What is the distance for each one? Also, quickly, I will present our novel technique, also entitled DM-AP1. This heuristic is dedicated for the assignment problem, and this technique is need just 3 sample steps, and this technique we will use a specific function, sum minus mean multiplied by n, where n is the number of objects, and divided by 2. So if I have 4 jobs which will be affected to 4 machines, what is the best assignment of the job to this machine? So here we are looking to generate a network diagram. So the DM-AP1 can easily generate this network diagram using just 4 steps. Okay, to conclude, in my presentation, I present the concept of the dhouib-matrix. Dhouib-matrix is a new kind of optimization algorithm or methods which gather heuristic and meta-heuristic. Today, I should use step-by-step application to generate, or how we can find the shortest drilling path in printed circuit board. This problem is classified as a TSP problem, but which is highly complicated. And here some of our method. In fact, all these methods are invented and designed and developed in 2021, and we are still working on this method, and we need to prove that this method are agile, flexible, robust, and therefore we have many perspectives with this technique. For example, we generate the heuristic. We have a new publication about the dhouib-matrix AP1, and we will iterate the DM-AP1 with the Fortunier in the DM4 multi-structure, and to look to generate how we can assign electric companion placement in printed circuit board. And also we look to develop other new heuristic and meta-heuristic for the short path problem, for scheduling problem, for knapsack problem. Thank you for your attention, and welcome for your comments and remarks.
Thank you.